Here, I would like to talk about a very important point. I think most of you have a confusion. How can we distinguish between a metallic and non-metallic object? Let me start with a one-dimensional object. Let's take this object with length L, okay, and with a negligible thickness. We talk just about one dimension. In this case, if this object is metallic or non-metallic, we have to use lambda as a coefficient of charge density. Okay, so here in the case of one dimensional object, we use lambda. And the relation between the charge of the object and lambda equals to the integral of lambda dl. Okay, this relation is used in the two cases, metallic and non-metallic. So here we have, in the case of metallic or non-metallic. Okay, now the question is, if Q is uniformly distributed inside the object or non-uniform distributed inside the object. Okay. In the case of uniform distribution, what I mean for each element of this object, we have the same quantity of charge. Okay. So here we have, for example, 5 coulombs. Here we have 5 for the same length. Here we have 5. So lambda, the charge density, is constant along the length of the object. So in the case of uniform distribution, here we have a constant value of lambda. So we can get out lambda here. We can write finally Q equals to lambda integral dl, and the integral of dl equals to L, so lambda L. In the case of non-uniform I mean, we don't have the same quantity of charge for each element. For this element here, we have 5 coulomb. For the same element here, that's the same length on the element on the object, we have 10. Here we have 100. Here we have nothing. So lambda is not constant along the length of the object. In this case, lambda depends on the length of the object, depends on the position. Lambda is not constant, and I give you a relation between lambda and the position. Let's take here, we have the length of the object along x-axis. Okay, so we can say, for example, lambda equals to constant times x. I mean here, for x equals to 1, lambda equals to lambda 0. Lambda 0 is a constant value. Okay. For x equals to 2, lambda equals to lambda 0. So lambda will change in terms of the position. Here you have to use lambda here, and you substitute its value in terms of the position. We get here, for example, lambda 0 x, and we have dl in terms of the x-axis. So dl in this case equals to dx, okay? And we can solve q. Okay, let me resume here. In the case of one dimension, we have a one-dimensional object. We use lambda in the two cases, metallic or non-metallic. But here, maybe you have a constant value of lambda, I mean uniform distribution of charge, or non-constant value, okay? You can write Q equals to lambda L, or Q equals to integral of lambda dl, okay? Now, let's take an example of a two-dimensional object, okay? For example, here we have a paper. You know, we have only two dimensions. A times B is the area of this object with a negligible thickness. Or we have a disk, for example, this one, okay? This disk has a area of pi r square, okay? If we don't have the hole here, pi r square, with a negligible thickness. In this case, if we have a metallic or non-metallic object, in the two cases, we have to use sigma as a charge density, coefficient of charge density. So we can write, in the case of two-dimensional object, we use sigma. And the relation between sigma and the charge, Q equals to the integral of sigma dA. In the case of metallic and non-metallic. Conducting and non-conducting object. Okay. Here we have a uniform or non-uniform distribution of charge on the object. In the case of uniform, like in the case of lambda, I mean you have for each element, for example, in this case, we have an element like this. For each element here, we have the same quantity of charge. On this element, we have, for example, 5 coulombs. Here also 5 coulombs. Here all 5 coulombs. So we can say here we have a constant value of sigma. So Q equals to, we get out sigma, the integral of dA equals to A. So we have a sigma A. And in the case of non-uniform, here sigma is not constant, okay? Sigma is not constant. So I give you some relation between sigma and the area. For each area or for each position on the area, we have a value of sigma. Okay, it will be given. So we have to use Q equals to sigma dA, and I give you the value of sigma in function of A. Okay, it's a given. So let me resume. In the case of two-dimensional objects, if you have a metallic or non-metallic object, you have to use sigma. In the case of a uniform, sigma is constant and Q equals to sigma A. In the case of non-uniform, sigma is not constant and Q equals to the integral. Let me talk about the third case if we have a three-dimensional object. I give you an example of a metallic object like this conducting object is a sphere of metal, and we can use a non-conducting object, non-metallic object. In the case of metallic object, the charge of the object will be distributed on the external surface of the object. Okay, so in this case we have to use sigma because we have a surface charge distribution. And in the case of a non-conducting object, non-metallic object, the charges will be distributed at any point inside the object. So we have a volumic charge distribution. In this case, we talk about rho. So we have a surface charge distribution. We talk about sigma, and we have a volume charge distribution rho. We can write here in the case of three-dimensional object, we can classify the objects between metallic and non-metallic. In the case of metallic, as we said, we have a surface charge density. It means I have to use sigma, okay? And in the case of non-metallic, charge non-metallic object, here we have a volume charge density rho. Okay, so the Q in the case of metallic object equals to the integral of sigma dA. Okay, and now it depends to the object. Maybe sigma is uniform or non-uniform. For example, in the case of uniform, when we have a uniform, I take an example of a sphere. In the case of sphere, you know the charge will go away from the center, okay? As the distance between the center of the object and any point on the surface is the same, so we'll get a uniform charge distribution, okay? In this case, we have a sigma equals a constant value. Sigma is constant. In general, like a sphere, okay? For example, sphere or a spherical shell, okay? We have many examples. In this case, when we have a uniform charge distribution, we can get out sigma. Sigma is constant, and the integral of dA equals to A. We can write Q equals to sigma A. In the case of non-uniform object, here, in the case if the object is not symmetric, this one is symmetric, okay? In the case of non-symmetric object, imagine you have the same object, but it's like a rectangle, okay? Let's take this one an object, three-dimensional object. But here, if this object is a metallic object, the charges will move away from the center. So as you see, the charges will be collected at the corner of the object, here, 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 and here, okay? And here we don't have charge. Here we don't have charge. Here we don't have charge, okay? So in this case, we don't have a uniform charge distribution, okay? So uniform and non-uniform, it depends to the form of the object. If the object is symmetric, we have a uniform charge distribution. If it's not symmetric, we have a non-uniform charge distribution, okay? So we can say non-uniform, like a rectangular or cubic volume. Now I take metallic object, okay? In this case, sigma is not constant, and I give you some relation between of sigma, a value of sigma. We get Q equals to sigma d A. I give you the value of sigma, and we calculate the integral, and so on. We can use Gauss's law in your calculation. Okay, this is about the metallic object. You have two cases, uniform and non-uniform. Let me take the case of non-metallic object, like this ball. In this ball, as we have a non-metallic object, the charge Q will be distributed inside the object, okay? So at any point inside the object, you have a charges, but I don't know if this charge is uniformly distributed or not. I don't know, but I know that we have a volumic distribution, volumic. So in this case, we talk about rho, and the relation here, Q equals to rho dV, because we have a volume of charge, inside. Now I tell you, maybe rho is constant. If rho is constant, we have a uniform charge distribution. If rho is not constant, you have a non-uniform charge distribution, okay? In the case of uniform, rho is constant. And you get out rho from the integral. We get Q equals to rho times V. V is the total volume of this charge, okay? And in the case of non-uniform distribution, in this case, lambda is not constant, rho is not constant. I give you some relation of rho. Maybe rho depends to the angle. we have this sphere, and for each angle we have a density. Okay, we have to substitute the value of rho in the relation. We get here in general Q equals to the integral of rho dV, and you do the calculation. In general, let me resume. In general, in the case of 3 dimension, you have to talk about metallic or non-metallic. In the case of metallic, the charges will be out of the center. We don't have in the body any charge. But about the uniform and non-uniform, it depends the shape of the object. If the shape is symmetric about the center, here in this case we have a uniform distribution. Sigma will be constant. And if the object is non-symmetric, like this object, in this case we can say that sigma is not constant. And in these cases, in the case of metallic object, we have to use sigma. Okay, we don't have the choice, you have to use sigma. And in the case of non-metallic object, you have to use rho, because we have a volumic distribution. But the about the uniform and non-uniform, it depends to the value of rho. If we have a uniform distribution, we have a constant value of rho. In this case, Q equals rho V. If rho is not constant, we have a non-uniform distribution. We use Q equals to integral rho dV. Please listen again the video. You have to understand well each case. If you have the problems, each case, you have to understand if we have a one-dimensional object, two-dimensional objects, we have a three-dimensional object, and for each case, you have to know very well if you have a uniform, non-uniform, you have to use sigma or gamma, sigma or rho. You have to understand well. Maybe it's important to solve any problem. If you don't understand if you cannot distinguish between the metallic and non-metallic, between uniform or not, it's difficult to solve the problem. Okay? Thank you.